It was 1967. Off the coast of Sinai, the Israeli destroyer INS Eilat patrolled 12 miles from Port Said, steaming slowly through calm Mediterranean waters. Her captain stood on the bridge, scanning the horizon through binoculars. The afternoon sun was beginning its descent, casting long shadows across the deck. The crew was relaxed. They had conducted this patrol dozens of times. Egyptian naval forces rarely ventured from port, and when they did, Israeli ships detected them long before any threat materialized. At 5:26 p.m., a lookout spotted a thin contrail on the horizon. The captain assumed it was an aircraft. Egyptian MiGs occasionally buzzed Israeli vessels, testing response times and gathering intelligence. The crew went to alert stations, tracking the contact visually. But something was wrong. The contrail wasn't climbing or maneuvering like a jet. It was flying straight and level, barely above the water, moving faster than any aircraft should at that altitude. Then struck. The SSN-2 Styx missile hit the Eilat amidships, punching through the hull and detonating inside the engine room. The explosion killed dozens instantly and flooded 2 compartments. Survivors scrambled to contain the damage, but before damage control teams could respond, a second missile arrived. Then a third. The destroyer listed heavily, her keel broken, fires raging below deck. 2 hours later, INS Eilat sank. 47 sailors died, 91 were wounded, and naval warfare changed forever. What stunned observers wasn't just that a destroyer had been sunk by missiles. That was a theoretical possibility everyone acknowledged. What stunned them was how the missiles had attacked. The Styx flew at 25 feet above the water, far below the coverage of the Eilat's radar. The ship's lookouts saw the missiles only in the final seconds before impact. By then, it was too late for evasive maneuvers, too late for countermeasures, too late for anything except damage, control. The destroyer never had a chance. British Royal Navy analysts received the intelligence reports within 48 hours. They pored over survivor testimony, examined photographs of the wreckage, and reconstructed the attack timeline. The conclusion was inescapable and deeply troubling. The Soviets had developed an anti-ship missile that could defeat Western naval defenses. The question that haunted every destroyer captain from that moment forward was simple. If radar couldn't detect a sea-skimming missile until the final seconds, how could anyone defend against it? The answer would require rethinking everything the Royal Navy thought it knew about naval warfare. If you want to understand the hidden revolutions that transformed modern combat, subscribe now. This is the story of how one Soviet missile made the world's most powerful navies obsolete overnight. Let's go back to 1958. The SSN-2 Styx began as a Soviet response to American carrier dominance. In any future war, Soviet naval planners assumed American carrier groups would control the seas. Soviet surface ships couldn't compete. The U.S. Navy had more carriers, better aircraft, and decades of operational experience. Soviet admirals needed a way to strike American ships without getting close enough for American aircraft to destroy them. The solution was a missile that could be launched from small, fast patrol boats. Soviet engineers at the Zvezda Design Bureau studied German wartime research on guided missiles and began developing a turbojet-powered anti-ship weapon with a range of 25 miles. The missile would be guided by a radar seeker in its nose, allowing it to home in on the largest radar return in its field of view. Simple, reliable, and cheap enough to mass-produce. The first tests in the Black Sea were encouraging. The Styx could hit target ships reliably in calm conditions. Its warhead, 1,000 pounds of high explosive, was large enough to cripple a cruiser, and its speed, just under Mach 1, made interception difficult with the anti-aircraft guns of the era. Soviet planners envisioned swarms of missile boats overwhelming American defenses through sheer numbers. But there was a problem. Early Styx missiles flew at high altitude, making them easy to detect on radar. Western destroyers equipped with long-range search radars could spot incoming missiles at 15 or 20 miles and maneuver to evade them. The missile's radar seeker was also unsophisticated. It locked onto the first large target it detected, which meant chaff or decoys could confuse it. Soviet engineers needed to make the missile harder to detect and harder to evade. The breakthrough came from an unexpected direction. Radar performance degrades near the ocean surface. This is caused by something called the radar horizon. The curvature of the Earth limits how far a radar can see low-flying objects. A destroyer's radar antenna, mounted perhaps 40 feet above the waterline, can detect a high-flying aircraft at 100 miles, but a missile flying at 25 feet? The radar horizon is only 8 or 9 miles. Soviet designers realized that if they could make the Styx fly that low, they could cut Western radar detection ranges by 2/3. The engineering challenge was formidable. Flying at 25 feet above a moving ocean requires constant altitude adjustments. Waves rise and fall. The aircraft, or in this case the missile, has to sense those changes and respond instantly. Too high, and you become visible to radar. Too low, and you crash into the water. The margin for error is measured in seconds and single-digit feet. Soviet engineers developed a radio altimeter specifically for the Styx. The altimeter transmitted a continuous signal downward and measured the time it took to bounce back from the water's surface. A feedback loop connected the altimeter to the missile's control surfaces. If the missile climbed too high, the controls pushed it down. If it dropped too low, they pulled it up. The system worked autonomously, requiring no input from the launch platform once the missile was in flight. Testing began in 1961. Early attempts ended in failure. Missiles crashed into the sea. Control systems oscillated wildly, causing the missiles to porpoise up and down until they lost stability. The altimeter struggled with wave patterns, misinterpreting swells as altitude changes. Engineers refined the software, adjusted the control algorithms, and redesigned the altimeter's processing unit. By 1963, the system worked reliably. The upgraded Styx, designated P-15M, could maintain an altitude of 25 feet across all but the roughest sea conditions. Its flight profile was programmed to cruise at high altitude during the initial phase, allowing the launch platform's radar to guide it toward the target, then drop to sea-skimming altitude for the terminal attack. This combination maximized range while minimizing detectability. Soviet naval doctrine embraced the new weapon enthusiastically. Komar and Osa-class missile boats, small and fast, carried 2 to 4 Styx missiles each. They could hide in coastal waters, dash out to launch range, fire their weapons, and retreat before Western forces could respond. In a war, dozens of these boats would swarm American carrier groups, launching missiles from multiple directions simultaneously. Even if only a fraction got through, the damage would be catastrophic. Western intelligence knew about the Styx, but they underestimated it. British and American analysts assumed the missile was too primitive to pose a serious threat. Soviet electronics were crude compared to Western systems. Soviet guidance technology lagged behind, and Soviet naval tactics emphasized quantity over quality. Swarm attacks that would be vulnerable to coordinated air defense. The consensus was that modern destroyers equipped with radar-directed guns and surface-to-air missiles could handle the threat. The sinking of the Eilat proved them wrong. Egyptian missile boats armed with Styx had waited until the Israeli destroyer was close to shore, where coastal clutter would confuse radar returns. They launched from port, fired their missiles at maximum range, and withdrew. The Styx missiles climbed to cruising altitude, flew most of the distance under radar guidance from the Egyptian boats, then dropped to sea-skimming mode for the final approach. The Eilat's radar detected nothing until the missiles were less than 2 miles away. At that range, traveling at Mach 0.9, the missiles arrived in less than 10 seconds. The ship's 40mm anti-aircraft guns couldn't traverse fast enough to engage. There was no time to launch chaff, no time to radio for help. The crew could only watch as the missiles closed. 4 missiles were fired, 3 hit. 1 destroyer sank. The British Admiralty convened an emergency session to assess the threat. Royal Navy destroyers relied on Type 965 and Type 992 search radars, both optimized for detecting aircraft at medium to high altitudes. Against sea-skimming missiles, these radars were nearly useless. The radar horizon meant detection ranges dropped to 5 miles or less than 30 seconds of warning time. British destroyers carried radar-directed 4.5-inch guns and Sea-Cat surface-to-air missiles, but neither system could engage targets that close and that fast. The Royal Navy's entire surface fleet was vulnerable. Admiralty planners ran simulations. In a war with the Soviet Union, British destroyers operating in the North Atlantic or Mediterranean would face swarms of missile boats and aircraft launching Styx missiles. Even with optimal radar performance, ships would detect incoming missiles only in the final moments before impact. Engagement windows would be measured in seconds. Hit probabilities were abysmal. The conclusion was stark. Without new defensive systems, Soviet anti-ship missiles would decimate NATO naval forces. British engineers began developing countermeasures immediately. The first priority was improving radar detection. Low-altitude coverage required different radar frequencies and different antenna designs. The Type 909 fire control radar, already in development for the Sea Dart missile system, was optimized for tracking low-flying targets. But radar alone wasn't enough. Even with perfect detection, engagement times were too short. The solution required faster reaction speeds and automated systems. The Sea Dart missile, paired with the Type 909 radar, could engage targets at ranges up to 15 miles. More importantly, the system was designed for rapid reaction. From detection to missile launch, the process took less than 20 seconds. A computerized fire control system calculated intercept solutions automatically, removing human decision-making from the loop. Operators simply authorized the engagement. The system did the rest. But Sea Dart wouldn't be operational until the mid-1970s. In the meantime, British destroyers were vulnerable, and everyone knew it. The Soviet Navy expanded its Styx production rapidly after 1967. By 1970, over 200 missile boats carried the weapon, deployed from the Baltic to the Pacific. Larger Soviet warships, including Kryvak-class frigates and Kashin-class destroyers, were equipped with upgraded versions of the missile. And Soviet naval aviation began integrating the Styx onto Tu-16 Badger bombers, giving the weapon an airborne launch platform with vastly extended range. NATO's nightmare scenario was taking shape. Soviet doctrine called for coordinated strikes using multiple platforms. Bombers would launch Styx missiles from long range, forcing NATO ships to defend against attacks from the air. Simultaneously, submarine-launched torpedoes would threaten from below, and missile boats would dash in from coastal waters to launch point-blank attacks. NATO defenses would be overwhelmed by the sheer number of simultaneous threats. British and American strategists studied the problem obsessively. The U.S. Navy accelerated development of the Aegis combat system, which used phased array radar to track hundreds of targets simultaneously and coordinate missile defenses. But Aegis wouldn't be operational until the 1980s. In the 1970s, NATO ships had to rely on older systems designed for a different threat. Close-in weapon systems became the new priority. If radar detection came too late for missile engagement, then the final line of defense had to be rapid-fire guns. The Dutch Goalkeeper system and the American Phalanx CIWS both used radar-directed rotary cannons firing thousands of rounds per minute. The idea was simple. Saturate the airspace around the ship with so much lead that incoming missiles would be shredded before they could hit. Testing showed the concept worked, sometimes. Against a single missile, CIWS had a high kill probability. Against 2 missiles arriving simultaneously from different directions, the odds dropped. Against 4 or 5 missiles in a coordinated attack, the system was quickly overwhelmed. Soviet doctrine called for exactly that kind of saturation attack. British captains trained their crews for worst-case scenarios. Exercises simulated Styx attacks with drones flying at wave-top height. Crews practiced emergency maneuvers, chaff deployment, and rapid-fire procedures. But everyone understood the grim mathematics. If Soviet missile boats launched a coordinated attack, some missiles would get through. Ships would be hit. Sailors would die. The psychological impact was profound. Destroyer captains who had spent their careers confident in the superiority of Western technology now faced a threat they couldn't reliably counter. Soviet missiles, built with supposedly inferior electronics and crude guidance systems, had negated decades of Western naval advantage. The sea-skimming capability didn't require revolutionary technology. It just required thinking differently about how missiles could be employed. That was the real lesson of the Styx. The Soviets hadn't built a better missile in absolute terms. Western anti-ship missiles like the French Exocet and the American Harpoon eventually surpassed the Styx in range, accuracy, and sophistication. But the Soviets had built a missile that exploited a fundamental weakness in Western naval defenses. They had turned radar, the technology Western navies relied on for situational awareness, into a liability by flying below its effective coverage. It was an asymmetric approach that reshaped naval warfare. By the mid-1970s, every major navy in the world was developing sea-skimming anti-ship missiles. The French Exocet, used by Argentina to sink HMS Sheffield in 1982, flew at 10 feet above the water and had a range of 40 miles. The American Harpoon could be launched from ships, submarines, or aircraft and used sophisticated radar seekers to home in on targets. Even smaller navies acquired these weapons, leveling the playing field against larger, more powerful fleets. The age of the battleship, already ending, was truly over. Large surface combatants became targets rather than assets. Their size made them easy to detect. Their radar cross-sections were enormous. A single Styx-type missile could cripple a cruiser. 2 or 3 could sink it. Naval architects began designing smaller, faster ships with reduced radar signatures. Stealth became as important as firepower. The Royal Navy redesigned its entire surface fleet around the Styx threat. Type 42 destroyers commissioned in the 1970s carried Sea Dart missiles and advanced radar systems specifically optimized for low-altitude detection. Type 22 frigates added Sea-Wolf point defense missiles for close-in protection. And every new ship design incorporated electronic warfare suites to jam or deceive incoming missile seekers. But the fundamental problem remained. Sea-skimming missiles were hard to stop. Even with modern radar, detection ranges against missiles flying at 25 feet were limited to 8 or 10 miles. At Mach 0.9, that gave defenders less than 40 seconds to detect, track, and engage the threat. Human reaction times consumed precious seconds. Computer processing added delays. By the time a defensive missile launched, the incoming weapon was already close enough that a kill might not prevent debris from hitting the ship. The solution required layers of defense. Long-range systems like Sea Dart or Standard missiles engaged threats at maximum distance. Medium-range systems like Sea-Wolf provided a second layer. Close-in weapon systems offered a last-ditch defense. And electronic warfare systems tried to seduce missile seekers away from the real target. Every layer had to work perfectly. One failure, and the ship was hit. In 1982, the Falklands War proved how dangerous sea-skimming missiles had become. HMS Sheffield, a Type 42 destroyer, was struck by an Exocet missile fired from an Argentine Super Étendard aircraft. The missile hit the ship's side, and although its warhead failed to detonate, the remaining rocket fuel ignited fires that spread uncontrollably. 20 sailors died, and the ship was abandoned. Later, HMS Glamorgan was hit by a land-launched Exocet and severely damaged. British forces lost multiple ships to sea-skimming missiles, despite having some of the most advanced naval defenses in the world. The lesson was brutal and clear. Even the best defended ships were vulnerable. Soviet observers studied the Falklands carefully. Their missiles had validated a doctrine developed 20 years earlier. Small, cheap weapons could threaten billion-dollar warships. Quantity could overwhelm quality. And sea-skimming technology made defense nearly impossible. The Cold War arms race intensified. Western navies poured resources into better radar, faster missiles, and more effective close-in defenses. The Aegis system, when it finally became operational, represented a quantum leap in capability. Its SPY-1 phased array radar could track over 100 targets simultaneously and guide multiple defensive missiles to intercept them. But even Aegis had limitations. In saturation attacks, where dozens of missiles arrived simultaneously, the system could be overwhelmed. Soviet missile technology kept pace. The SSN-22 Sunburn, introduced in the 1980s, flew at Mach 2.5 in its terminal phase and maneuvered violently to evade defenses. The SSN-27 Sizzle combined sea-skimming with supersonic speed. Each generation of Soviet missiles became faster, more maneuverable, and harder to stop. Western defenses improved, yes, but the fundamental advantage belonged to the attacker. That advantage persists today. Modern anti-ship missiles fly even lower, even faster, and use artificial intelligence to identify targets and plan attack routes. Hypersonic missiles travel at speeds that make interception nearly impossible. And the basic principle established by the Styx in 1967 remains unchanged. The ocean surface provides cover that radar struggles to penetrate. The Royal Navy destroyer captains who were baffled in 1967 would recognize the problem their successors face today. The SSN-2 Styx was never the most sophisticated weapon in the Soviet arsenal. It wasn't the longest range or the most accurate or the most technologically advanced, but it was effective. It exploited a weakness Western navies hadn't anticipated and couldn't easily counter. And it proved that in modern naval warfare, the missile was king. Here's the killer statistic. From 1967 to 1990, no Western Navy developed a reliable defense against coordinated sea-skimming missile attacks. Improvements were made, yes. Radar got better, missiles got faster, but in simulations and exercises, saturation attacks consistently overwhelmed defenses. Ships were hit, ships were sunk. The Styx changed naval warfare forever. It forced navies to abandon the surface-dominant strategies that had defined naval power since the age of sail. It made large surface combatants vulnerable. It gave small nations with limited budgets the ability to threaten superpowers. And it established a template for anti-ship missiles that every nation has followed. The sinking of the Eilat in 1967 wasn't just the loss of one destroyer. It was the end of an era. Naval warfare had entered a new age, where missiles mattered more than guns, where electronics mattered more than armor, and where a cheap Soviet weapon launched from a small patrol boat could sink a modern warship. British destroyer captains learned that lesson the hard way, through intelligence reports and simulations, and the cold knowledge that their ships were vulnerable. Soviet missile boats were out there, lurking in coastal waters, armed with Styx missiles that could strike without warning from below the radar horizon. That's a threat no captain could ignore. If this story revealed something you didn't know about naval history, subscribe now for more deep dives into the weapons and technologies that shaped modern warfare. Next time, we'll examine how submarine-launched cruise missiles changed the nuclear balance. Thanks for watching.